Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Vikram Gadagkar, who is Assistant Professor of Neuroscience at Columbia University. His research focuses on learning, memory, and computation. Welcome, Vikram.
Great to be here, Gil.
Yeah, so thanks for doing this. I want to start with one of your papers entitled Dopamine Neurons Encode Performance Error in Singing Birds.
Yeah.
And you say many behaviors are learned through trial and error by matching performance to internal goals, yet neural mechanisms of performance evaluation remain poorly understood. And this has always been sort of a mystery, right? Increasingly we have this deep learning networks in the artificial intelligence world, and performance evaluation is always a difficult thing in silicon. But you have an experiment here in singing birds that might give us some insights.
Yeah, exactly. So actually, let me give you a little bit of a context for this, right? So as you mentioned, practice or trial and error learning is extremely important, and we do it all the time. So I don't know, do you play music? Do you play music or sports or anything like that?
I used to play some sports, but not much music. Yeah.
Yeah. So if you're even just learning how to speak or play a musical instrument or anything like that, we know that practice is extremely important. We're not born being able to perform these tasks, and we learn them by practice or trial and error. And the question we were interested in is, how does the brain actually get better with practice, right? So what happens in the brain while you're practicing? And so the way we think about practice, I'm going to use trial and error and practice sort of interchangeably.
Yeah.
And that's because when we're practicing, what we're really doing is in a sense, trial and error. So let's say you're trying to play the piano, you're trying to practice a piece on the piano. You play something, and then you listen to yourself play, and then you ask yourself, did I do the right thing, right? And if you did the right thing, then you want to do the same thing again. But if you did not play the right note, then you don't want to repeat your mistakes. So there's a trial phase, and then there's a comparison, and then there's an error phase. Right. And so one big question that you can ask, if this is true, that if you're actually learning by trial and error, one question you can ask is, where is the error signal, right? So there must be some part of your brain that contains this error signal that tells the rest of the brain whether you did a good job or not.
Yeah, and really fascinating. So for that to work, for the brain to identify something to be an error, there be an expectation, right?
Right. Exactly. Yeah. Exactly. You're absolutely.
And so is it people don't like going back to the computing world, but we have a similar sort of a process in neural networks, artificial neural networks, where
Right.
you train it and you look at the errors, and those errors give you guidance as to how to train better. And
Exactly.
it sounds like the brain is doing something sort of similar.
Yeah, exactly. So I think let me answer your first question about what the birds are actually doing,
Yeah.
and that will connect us to what we can do with artificial neural
Yeah.
networks. So going back to the question of how do we find this error signal, the way we went about doing this was we used the songbird. So these are zebra finches that we study
Yeah.
as a model system. And the reason zebra finches are such a good model system to understand trial and error learning is because they also seem to learn their song by trial and error.
Yeah.
So when a baby finch is born, it doesn't know how to sing. All it can do is babble, just like a human infant. And it turns out that the father finch sings a song to the baby finch, and the baby listens to the father's song, remembers the father's song,
Yeah.
and then starts babbling in an attempt to make a copy of the father's song. And after 2 to 3 months, over the course of 2 or 3 months, the babbling progressively gets better and better. And at the end of that time, the finch is able to sing very similar to how the father used to sing.
Are these
Right?
songs, do they have information, Vikram, or is it just a song? Are they actually communicating through the songs?
So that's a great question, and and actually we should, that's more in we could speculate on that
Yeah.
maybe a little bit later, but that's a great question in terms of what information content is in the song,
Yeah.
and what are they actually trying to communicate. And some of our future research directions are actually going to be looking into that, especially in terms of what the so the so going back to the song, the reason these birds learn to sing is so they can ultimately attract a female, right? So in this species, only males sing
Yeah.
and females don't sing. And so the male learns his song and he sings to a female and to attract the female. It's a courtship song,
Yeah.
right? And so you can ask, what is the female looking for in the song, and what does she find attractive? But I think we should come back to that a little bit later after I've sort of addressed your first question.
Yeah. Um,
So
it,
sorry, go
it
ahead.
makes sort of intuitive sense. So there is a lot of cost here, right? The baby is spending a lot of time
Mm-hmm.
by trial and error trying to learn this. Obviously, there is a utility here, uh,
Right.
and and one utility, obviously, as you mentioned, is a courtship requirement, and then the question of whether there's additional information in there is still being investigated. Uh,
Yeah.
so going back to the paper, then you're finding. So before we get to the details, what exactly are dopamine neurons?
Yeah. So dopamine is what you might call a neurotransmitter.
Yeah.
So it's a chemical that is released by certain neurons in the brain, right? And so these neurons that release this chemical dopamine are called dopamine neurons or dopaminergic
Yeah.
neurons. And there are other neurotransmitters in the brain. There are you have glutamate, for example, that's excitatory, and there's GABA, which is often inhibitory. And these are the more common neurotransmitters. But dopamine is what you might call a neuromodulator.
Yeah.
So dopamine can have downstream effects on other neurons that receive this chemical. And so it can modulate the neural activity of downstream neurons. And you might have heard, dopamine has been popularized in the media as a happiness chemical, if you will. So yeah, dopamine has received a lot of interest in the last few years, because it's involved in motivation, it's involved in trial and error learning, and it seems to be involved in a lot of different aspects of brain function.
So there is some sort of a reward reward mechanism, right? The brain likes dopamine.
Exactly.
And,
Exactly. So, yeah, sorry, go
yeah,
ahead.
go ahead.
Yeah, you touch upon a very important point. And in fact, this is the reason that we did this experiment in Songbird. So this was the reward aspects of dopamine was the motivation for us to do this experiment. So let me briefly tell you what was known about dopamine. So there were classic experiments as early as 1950s by Olds and Milner that showed that if you allow a rat to self-stimulate his own dopamine
Yeah.
neurons, he likes that very much. So let's say you put a rat in a box with a lever, and if he presses the lever, he gets to self-stimulate his own dopamine neurons. Rats love doing that. And in fact, they like it so much that they keep pressing the lever to the exclusion of everything else. They don't want to eat, they don't want to have sex. They just keep pressing the lever. And some rats are known to even die because they just don't do anything else. Right? So,
Sort of.
sorry?
It's addictive.
Yes, exactly. It can become addictive. So it's so rewarding that it can become addictive. And then the next big clue to what dopamine might be doing came from classic experiments from Wolfram Schultz and colleagues working on monkeys that showed that dopamine neurons encode what is called a reward prediction error. So, like, what do I mean by that? So, let's say you have a thirsty monkey, right? And if the thirsty monkey unexpectedly gets some juice, so he's not expecting juice, but he's very thirsty, and suddenly, unexpectedly, he gets a little bit of juice. If this happens, then his dopamine neurons show an increased activation, right? So his dopamine neurons fire to unexpected rewards.
Yeah.
Similarly, if the monkey is expecting a reward, but he does not get it, right? In that case, these same dopamine neurons stop firing. So they're suppressed.
Right.
So you can think of it as whenever something unexpectedly good happens, these neurons increase their firing. And when something unexpectedly bad happens, they decrease their firing. And usually in terms of external rewards like food or juice or stuff like that.
Yeah, so I was thinking, Vikram, from an evolutionary perspective, it is not clear why this. Maybe I'm not understanding. So, if the brain gets some sort of a reward mechanism fired, because of an
Yeah.
unexpected outcome,
Yeah.
it doesn't have any sort of conditioning effect, right? Does it have survival benefits that we can think of if it is, if the input was totally unexpected?
Yeah, no, I think that's a great question. And I think it does. I think it's a very clever system that actually uses this expectation. And I think it'll be easier for me to explain why it is so if we talk about the songbird experiment, and then it'll sort of follow from that. So the question we wanted to know was, so let me take a step back and just say that the reason this idea of a reward prediction error is so important in neuroscience is because we think that this is a learning signal, right? So let's say you have a rat in a box again, and there's a lever, right? And whenever the rat presses the lever, he gets a food pellet, right? Now, if you do this experiment, if you just put a rat in a box with a lever and you let him be, he's going to try various things, and he's going to figure out by trial and error that he should press the lever, right? Now, how does this happen? So he's exploring the cage. He doesn't know what's going on. He does various things, and by chance he presses the lever. The moment he presses the lever, he gets a little bit of food.
Right.
That causes this dopamine spike. And what the dopamine increase is telling the brain is whatever you just did was great. Do that again. So dopamine has a reinforcing effect on whatever the rat just did. And that's why it's involved in reinforcement learning, as you were mentioning earlier.
Yeah. So does it have a memory effect also, Vikram? So I'm going back to Homo sapiens 50,000 years ago. By
Yeah.
accident, he or she found a water hole.
Yes.
And prior to that, they looked for a big tree or something. And so there's a set of features that reinforces that the probability of finding water has increased or something along those lines, right? So,
Yes,
yeah.
exactly. So what we think, what neuroscientists think is going on, is that what dopamine is able to do is it is able to connect the context to the outcome.
Yeah.
So the context, the action, and the outcome. So in your example, so let's say they were, as you said, Homo sapiens thousands of years ago, they were wandering around in the savannah or whatever, right? And they saw a snake, right? Yeah. And how do you learn that a snake is dangerous, right? So looking at the snake is the context,
right?
So, and then let's say there was this person who had no idea if snakes were good or bad, and he happened to touch the snake just because of exploration, and the snake bit him.
Yeah.
And then it was very painful. So the idea is that looking at the snake is the context, the action is touching the snake, and the outcome is the pain that was caused by the bite. So when there is an unexpected pain, that can lead to a suppression in dopamine, right? And so the next time this person sees the snake, he is less likely to touch the snake.
So dopamine is sort of either positively or negatively reinforcing.
Exactly. So you can flip this, and you can say, let's say the same person is walking along in the forest and he sees a mango, right? Like a bright mango, and he doesn't know what it is. So he takes the mango and he bites into it, and suddenly he gets this burst of amazing flavor and sugar and what have you, and that can lead to a positive effect, and that can lead to an increase in dopamine, right? And so the next time he sees the mango, he's more likely to bite into it. And so, exactly as you said, dopamine can positively reinforce good or better than expected outcomes, and negatively reinforce bad or worse than expected outcomes.
And just this idea that you're getting either positively or negatively rewarded, I would imagine then has an impact on memorization of that context, right? So you start to remember really good things, really good situations, and really bad situations, and over time you learn about them.
Exactly. So we think that in the brain, the context gets wired up to the right action. So the next time you find yourself in this context, you don't have to think about what to do. Your brain automatically gets you to do the action that was most beneficial in previous trials.
Yeah, so I don't know. This is an experiment. We'll talk about the experiment in a minute. Yeah, I don't know if this is an experiment, but let's say you have many trials, and the brain has learned something by trial and error. Once it has learned, one could imagine, at least mechanistically, the dopamine doesn't have to be there, or that is not true.
So you're asking, so once you have learned something, then what happens, right? And so I think what happens is that even after you learn something, you still have to maintain it, right? So for example, let's say you said you played some sports, right? So let's say you're learning how to play tennis, right? And you practice a lot and you become really good at it, and you become a professional tennis player, right? Like, let's say, like Serena Williams, right? She's a professional tennis player, but even Serena needs to keep practicing, right? If she stops practicing, then slowly her game will deteriorate, right? So even after learning, to maintain the skill, you need to keep practicing. And that's what we find in the birds as well, that even after the birds have learned their song, they continue to sing, even when they're by themselves, they continue to sing. And what we think is going on is that we think that they're continuously practicing to maintain their song.
Yeah, yeah. So let's return back to the paper. So this is sequence,
Yes,
and the context is that the father is singing to the baby bird, and it doesn't get it right initially, and over time, over many trials,
exactly. Right,
it gets it
right.
right. And so during the experiment, you are actually measuring the dopamine release or inhibition.
Yes. So, okay. So here's so the reason we did the experiment was we were asking a question about the function of
Yeah,
dopamine, right? So what I told you so far, or at least in the earlier experiment, is that we already knew that dopamine was involved in this reward prediction error. So whenever you got food or juice that was unexpected, you had an increase in
yeah,
dopamine, right? And so scientists knew that dopamine was involved in reward based trial and error learning. The question we wanted to ask was, how does other kinds of learning happen? So, for example, we were talking about learning to play the piano or learning to play tennis or learning to speak, right? We don't do these things for primary rewards like food or juice, right? You don't learn how to speak better for juice rewards, or you don't learn how to play tennis better for food rewards, right? These are sort of naturally learned motor sequences that are learned by comparing ongoing performance to some internal standards, right? And so the question we were interested in is, does dopamine also play a role in the natural learning of such behaviors that have nothing to do with immediate food or juice
right,
rewards?
right.
And zebrafinch, the songbird is a great system to answer this, because zebra finches learn how to sing not for food or juice rewards, right? They have an internal template, which is the father's song, which they remember, and they are trying to achieve that song. So they're trying to make a copy of that song by learning how to sing.
Yeah,
And so that's sort of the question. And coming back to what you were asking in terms of what we actually
yeah,
did, okay, so what did we have to do? So we had to record from these specific dopamine neurons that we had hypothesized might encode what we later call a performance prediction error instead of a reward prediction
yeah,
error. We had to record from these neurons while the birds are singing, but we also had to do something else. We had to fool the birds into thinking that they made a mistake.
right. Yeah, yeah,
Right? Because if you're looking at very young birds, it's not clear whether they're making a mistake or not. And so what we decided is that we would study adult birds that have already learned their song, but we would fool them into thinking that they made a
yeah,
mistake. And the way we did that was we used a technique called distorted auditory feedback. So the idea is very simple. So let's say the bird has 4 syllables, A, B, C, D, for example. That sounds like chikwa. That's what it sounds like. And what we did is we take a part of a different syllable. So for example, you can take the first part of syllable A that sounds like ch and play it over syllable
yeah,
D using a speaker, right? So now the bird is singing along and he's singing chikwa, 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 chikwa. But what he is actually hearing is chikwa, 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 depending on whether or not we distorted syllable D with feedback.
yeah, yeah.
So does that make
Yeah,
sense?
yeah, yeah.
So
And so,
yeah,
uh, so the feedback, so it has to be sort of instant feedback, right? For it to recognize that is the sound it just made.
yeah, exactly. So what we do is that while the bird is singing, we are recording the
Yeah,
bird song, and we have a computer that is analyzing the bird song in real
yeah,
time, and we know exactly when syllable D is going to happen. And just before that, we toss a coin, and if it's heads, we distort syllable D, and if it's tails, we leave it alone.
okay,
So half the time we distort it, half the time we don't, and the bird has no way of knowing whether it's going to be distorted or not.
right, okay, okay. And so,
Okay.
so you have sort of a control, and you have a distorted signal going back, And so, so what do you find? What's the difference between the two?
Yeah, exactly. So now the question is, what do the dopamine neurons do when the song is distorted? Because the idea is that the bird clearly does not want to listen to a distorted syllable because it sounds different from what he wants to hear, so it sounds wrong. And do the dopamine neurons do anything special when this happens, right? That's the question. So we recorded these dopamine neurons, and we found that these dopamine neurons shut down their firing. So they're immediately suppressed after a distortion. So when the bird hears a distorted syllable, dopamine neurons are suppressed, which is exactly what we would have predicted based on the reward prediction error idea. Except now there's no external reward, right? It's just that the bird's performance did not match what it wanted to make. Right. So this was very interesting. But you can ask now, this is great, but what do the neurons do when the bird heard a syllable that was not distorted? So when the bird heard an undistorted syllable, what happens? Right? And here we found that the neurons actually increase their activity when the bird heard an undistorted syllable. Now this can be a little surprising, right? Because we didn't do anything to the song. Right? The song was completely untouched. It heard a syllable D that was perfectly produced, and yet the dopamine neurons increase their firing from their baseline. And so why does that happen? And that's where we get back to your earlier question about expectation. So what we think is going on is, because we were distorting syllable D half the time, the expected quality of syllable D had been lowered for the bird. So the bird now does not expect to sing syllable D well all the time, right? And so now when it hears an undistorted syllable D, even though it was completely untouched, it actually sounds better than expected to the bird. And that is what is being signaled by this increased dopamine activity on undistorted syllables.
Yeah, that is really interesting. So coin toss. So essentially you have an environment now, the bird has an expectation of 50% of a good signal and 50% of a bad signal.
Exactly.
And it hears a good signal, it has a sample, at 100%, and it's getting positive reinforcement, and negative side otherwise. So this is a system, Vikram. So essentially, it is what you're proving here is that it's a system that allows, whether it's a bird or a human, to learn from practice, to learn from trial and error. It's expected that you make mistakes as you learn, but when you do it correctly, you get a boost. When you do it incorrectly, you don't, and over time, that should lead you to a better learning posture. That is idea.
That exactly. So there are two sort of important points here, right? So the first point is exactly as you said. So the first point is that dopamine is involved in natural trial and error learning, independent of rewards. So independent of external rewards like food or juice. So this was sort of the first time that anyone had shown that dopamine-based reinforcement learning can happen without the involvement of primary rewards like food or juice. So that's the first sort of important point here. The second, which you alluded to, is that the birds are not just comparing their song to an ideal template, but they're actually comparing their song to what they expect to sing. Right? And that is, again, that goes back to a question that you were asking earlier. Why is this expectation important? What is the purpose of having an expectation? Why not just compare it to the ideal? Right? And if you think about it, I think this makes a lot of sense. So going back to our tennis analogy, right? let's say you're learning to play tennis and you're working on your forehand. Now, it doesn't really make sense to compare your forehand to Serena's forehand,
Right.
right? Because it's always going to be worse than Serena's forehand.
Yeah.
But it makes more sense to compare your forehand today to your forehand yesterday,
Yeah.
or how your forehand was last week.
Right.
Because then you can start asking, am I improving from where I was, or am I getting worse from where I was?
Right. Right.
And this will allow much greater sensitivity for learning than comparing it to an ideal that is very far away from where you are.
Yeah. I wonder if there is any sort of tolerance that sets in over time. So just like you're describing, as I become more and more expert at
Right,
something,
right.
I actually do I need less quantity of dopamine to marginally improve from where I am?
I don't
Yeah.
know if you need less dopamine, but I think what the system is allowing you to do is that you are now sensitive to small
Yeah.
changes around this new mean,
Right.
if you
Right.
will, right? And so it is increasing your sensitivity to learning. Because otherwise, what happens, right? If you're just looking at an error
Yeah.
from an ideal, then every time you sing, you're just really bad compared to your ultimate goal, like for a baby bird, for example, right?
Right.
And so your dopamine is always going to be suppressed, and that's not very useful.
Right.
But if you have improved from yesterday, even though that is a small change, by comparing it relative to where you were yesterday, you are getting much higher sensitivity to performance changes. And I think that is the beauty of the system, is that it allows you to make progress this way towards the ultimate goal.
Right. Right. And so again, going back to the bird experiment here, um, I, I don't know if this is in the paper, Vikram. So suppose you have some sort of repeating pattern, A B C D
Uh-huh.
A B C D A B C, distorted D, and then A B C D. So only the third sequence is distorted, and
Right.
you do that many times. So the bird now is thinking, for whatever reason, it cannot do the third one. um, and and do you find it so? What I'm asking is there a difference between random underperformance
Right.
to some sort of predictable underperformance?
Right. That's a great question. So we haven't done that specific
Yeah.
experiment, and it would be an interesting experiment to do. But the reason we did not do that particular experiment is we specifically wanted the distortions to be
Yeah.
unpredictable. So, because we didn't want the birds to have a prediction of exactly what's going to happen in that syllable D, and we wanted it to be probabilistic.
Yeah.
But I think we did a different experiment that sort of gets to your question in a different
Yeah.
way, and it also gets at your question about expectation. And this was the two target experiment that we talk about, like after the first
Yeah.
experiment. And so here the question is, so if it's true that they're actually developing an expectation of syllable D of their own
Mm.
performance based on recent practice, then we should be able to change that expectation depending on how often we are distorting the syllable,
Yeah.
right? So to test that, we did this, what we call a two target experiment, where now we distort two different syllables, right? So we distort syllable B and we distort syllable D. But the difference is that we distort syllable B half the time, 50% of the time, just like
Yeah.
before, but we distort syllable D only 20% of the time.
Yeah.
So the idea is that when the bird hears an undistorted syllable D, it's much less surprising for it because 80% of the time it's undistorted,
Right.
compared to when it hears an undistorted syllable B, which should be more surprising because that's only undistorted 50% of the time.
Yeah.
And so the prediction would be that there should be a higher dopamine burst when it listens to an undistorted syllable B compared to an undistorted syllable D. So, and that's exactly what we found. And so this is suggesting that birds are indeed keeping track of their recent performance and developing their expectation based on that and comparing their ongoing performance to that recent performance metric.
Yeah, it's a really complex modulation system, right? So this gives new meaning to the phrase, there's somebody in my brain, but it's not me. There is a system that's essentially trying to make you better.
Right.
And it doesn't appear to be a conscious system, right? It is almost instinctual that it.
Yeah, exactly. You get at a very interesting question there, actually. So I think what you're asking is, so one interpretation of your question could be, for example, when the bird happens to sing a note that's particularly nice, or let's say when it hears an undistorted D and it's better than expected performance. Does the bird actually feel happy as well? Is there an emotional valence associated with that, or is it all completely below the surface automatic learning? Right? And we don't really know the answer to this question. So we don't know if the birds are actually feeling some sort of happiness and sadness when they do better or worse than expected. But we do know that the learning happens.
Yeah, because there's also a memory question here, right? It has to remember what it actually did to get a good result, and so you have to store those instances that were good, good actions and good outcomes, with a higher probability of retrieval in the future. So there's definitely a memory question here too.
Right, or at least you need to store the probability of doing well somewhere in the brain and use that information to decide whether you want to have an increased dopamine or decreased dopamine. And in fact, one of my colleagues followed up on this work and he discovered that a different part of the brain is involved in computing this expectation.
Right, yeah. The brain is a scary place to be, that's for sure.
It is.
We'll take a quick break, Vikram. When we come back, we talk about your other paper.
Okay, sounds good.
Courtship context in singing birds. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So Vikram, we are back. We were talking about your paper on dopamine neurons and how they help learn from a trial and error process, or by practice. And we're talking about the zebra-finch experiment. You have another paper, dopamine neurons change their tuning according to courtship context in singing birds. You say attending to mistakes while practicing alone provides opportunities for learning, which we discussed in the first paper, but you say, but self-evaluation during audience-directed performance could distract from ongoing execution. So what do you find here?
Yeah, exactly. Right. So this was, so it was very interesting what motivated this project. So as I was mentioning earlier, as you said, we found this error signal in dopamine neurons that seemed to be important for practice. And then when I was telling my musician friends about this discovery, they told me that they treat mistakes that they make very differently during practice and performance.
Right.
So when they're practicing the song, they pay a lot of attention to their mistakes because they want to learn from their mistakes.
Right.
But when they have practiced their song and now it's the big day, they're on stage and they're performing to an audience, and then they make a mistake, then they don't want to pay a lot of attention to those mistakes. They might want to brush those mistakes under the carpet because the show must go on, right?
Yeah, wouldn't there be sort of an audience feedback issue here too? So if I use the audience reaction as a proxy for mistakes, then that would imply that I have sort of external stimulus coming back to me, right?
Yes, exactly. And that is, in fact, something that we're looking at in the future. So that's like the next direction that we're going in about, what does the audience actually do? But many of these mistakes, the audience might not even realize they are
Yeah.
mistakes, right? And and even if they do, you might not want to obsess over those mistakes because that might genuinely affect your ongoing performance. And so a lot of performers tell me that if they start thinking about the mistakes they made, then they ruin the rest of the song as well. And,
Yeah.
right?
I
And
can
so
also see, Vikram, the another problem. So if you perform in front of a sort of a non-technical audience who
yeah,
don't quite pick up on mistakes,
right.
you might actually get worse.
Oh yeah, no, yeah, for sure, yeah, for sure. It's a very complex system, right? About how we learn and how we perform and how we get feedback, and so we're trying to get at different elements in this process through the Songbird system, and so because my friends told me this, and this sort of made intuitive sense, if you will, we wanted to ask, is this what happens in the birds?
Yeah.
And the reason we can ask this, the reason the system is so well suited for such questions is, again, going back to what I was telling you earlier, that the reason these male zebra finches learn to sing is so they can perform to a female.
Yeah.
Right? It's a courtship song. So already in the system, we have a practice mode and a performance mode built in. And so it's perfectly suited to ask such questions.
Right.
And it even turns out that the song itself is a little bit more variable from rendition to rendition when they're practicing compared to when they're performing. So when they're performing, the song becomes extremely stereotyped, which means that every time the bird sings ABCD, he's singing it exactly the same when he's singing to a female. But when he's practicing, he's a little bit more variable, as though he's exploring the space a little bit for trial and error learning. So the system really looks like it goes from a practice mode to a performance mode.
Mm.
And so our experiment now is record these same neurons
Yeah.
while the bird is practicing, and then while the bird switches to performing to a female, and see what happens to this error signal that we found in the practice mode.
Right.
And when we did this, we found that the error signal that was there during practice was substantially reduced. It became much smaller when the bird was performing to a female, in line with what you would expect based on what my musician friends told me.
That
So it, in fact, sorry, go ahead.
sorry, Vikram. The error signal, meaning the dopamine action.
Yeah, so by error signal, I mean that the increase in dopamine on undistorted syllables and the decrease in dopamine after distorted syllables. So basically, the dopaminergic response to mistakes or worse or better than expected performance. This is what I'm calling the error signal, and this is what we think is being used as a learning signal in trial and error. This error signal becomes smaller and sometimes completely goes away when the birds are performing, and then they make a mistake.
Yeah, so two interesting observations, right? If I understand this correctly, Vikram, one is when they perform, they are making it's stereotyped. It is very rigid. So they have a template, and they're just following the template. They try to reduce the variance in that template during performance. And even if there is a variance, if I understand you correctly, even if there is a variance, you don't actually see a neuron positive or negative reinforcement, even if there is a variance, right?
During
During
practice or
performance.
performance? So during performance, okay. So sorry, let me take a step back. So I think I wasn't clear about this. So we're still doing the same experiment. Yeah. So we are still distorting syllable D half the time.
Oh,
right? So yeah, so whether they're practicing or they're performing, we are still introducing the same errors half the time.
But
the question is, how does the brain respond to these errors? Yeah, exactly. In these two different contexts.
Right. Yeah, so that makes intuitive sense, I guess, right? In some sense. So what is your explanation of that?
So what we think is going on is that this whole dopamine mediated, reinforcement learning happens through this learning system, right? And it involves the basal ganglia and the cortex and the thalamus and the dopamine neurons. It's like a whole learning system in the brain. And we think that this system is optimized for learning during practice.
Yeah.
And when the bird switches from practice to performance, this learning system is turned off, if you will, to make the brain optimized for performance. So we think that in these two different states, the brain is optimized to do two different tasks. So in the human context, for example, if you think about you're practicing a song, while you're practicing, your brain is optimized for learning. So you want to pay attention to your mistakes and you want to learn from them and you want to get better and better. That's what you're trying to do. You're trying to learn.
Yeah.
But once you have learned and now you're on stage and you're performing, then you don't want to be learning at that time.
Right.
On stage, you want to be putting out the best song that you've got, right? You want to be on your best game and you want to put out the best song that you possibly can. That's not the time to be learning.
Yeah, it makes really intuitive sense, but from a system perspective, it is really complex, right?
Yes.
And so it's a sort of it's switching off the learning system while performing. One could argue a mistake in performance is very costly, and so if you have some sort of a long-term learning process going on, meaning I screwed up here, but I'm going to get better next time around. I would imagine the learning system will continue to work, right? So, but that is not what you're finding in this context.
Well, so after the performance, then you can go back to practice. So for example, in this system, if we show a female so let's say a male bird is practicing, and then you show him a female, he immediately goes into this performance mode and sings his best song to the female, right? But then if you take away the female, he goes back to practicing. So it never ends. So he goes back to practicing and he keeps improving and maintaining his song until he has the opportunity to sing again to a female.
Right. Yeah. Yeah, and this idea that you mentioned before, that the practice mode is continuous, and so if you don't switch it on, even after you become an expert, if it is not functioning, then you tend to lose that over time, right? So this has always have to be there for it to.
Yes, I think I think it is actively maintained, and in terms of, it makes sense, right? Because, for example, you could think of various reasons for this, but one reason is that, let's say you've learned how to talk or how to sing, and then with age, right, your muscles change.
Yeah.
Right, your different muscles become weaker, and so if you don't maintain a motor skill, then it's going to deteriorate.
Yeah, the data.
So you need to
So you're getting new data, and not only new data, but also the reactions to the new data are all changing. So
exactly. The data, that's very important. So for example, in the birds, if you deafen birds, so if you prevent them from listening to their own song, then over time the song deteriorates.
Right.
So they need to keep listening to themselves to make sure that they're actually singing the way they want to.
Right. Yeah, I don't know if you have thought about this, Vikram, but do these observations have some impact on policy from an education perspective? Do you see any?
That's, yeah, I mean, that's a very broad and deep question, and obviously it's not my area of expertise. But I will say that getting the appropriate
Yeah.
feedback, right? The appropriate feedback at the appropriate
Hmm.
time is extremely important for for efficient learning. And so people are actually using some of these such ideas to develop better sort of teaching strategies. So, for example, you can imagine somebody trying to learn a particular task, right? Let's say they're trying to figure out how to solve something, or how to do a particular
Yeah.
task. If they make a mistake, if you're able to give them immediate feedback about that mistake,
Right.
then they will be able to learn much better than if you don't give them appropriate feedback, or if the feedback is very much delayed. So it turns out that the way the dopaminergic system works is that there is an optimal time
Yeah.
at which you need to get that feedback. And so I think in that sense, we must think very carefully in terms of education. Are we giving students the correct feedback, and the appropriate kind of
Right.
feedback that is actually helping them learn?
Yeah. I'm no expert in this area, Vikram. I'm just speculating here. It also sounds to me, if you abstract this, you say the brain comes with a basic operating system. And
Right,
part of that basic operating system is this learning process that you have demonstrated. And so if a student is left alone, this
right,
learning system, we know that this learning system is there, right? Move
right,
forward. Now, if you put some apps, so to speak,
right.
on that machine, if those apps are in conflict with this basic learning system, then that could that could lead to complications over time, I would think.
Yeah, absolutely, absolutely. I mean, I completely agree with you, and that's where I think it's very important to figure out the right kind of feedback as well,
The
right?
right
So
and
I
the
can,
right timing. One of the things
yeah,
that seems to be happening, countries like Finland and other Scandinavian countries, there seems to be going back from prescriptive education
yeah,
and essentially giving students more freedom to learn.
right,
And I often felt that in the US and other systems, we have gone in a direction that everything is sort of, very highly prescribed. And if you do
right.
that, perhaps systems like this that's already in the brain may not have a chance to perform actually.
Yeah, I think trial and error learning is extremely
Yeah.
powerful, right? And so I think allowing students to explore in a safe environment, I think can be very effective. And so I think the key here is that you want students to
Yeah.
explore without fear, right? So if you make a mistake, then you want to get the feedback that it was a mistake, but you don't want to get this massive negative
Yeah.
affect, right? Like you don't want to be disappointed
Yeah.
in so I think in a lot of education, what happens is that we punish
That's right.
mistakes,
Yeah.
right? And I think there's a big difference between punishing mistakes and giving feedback that it was a
Yeah.
mistake. So I think that is very important for effective education, because if you punish them, then they would not want to try, because you see what I'm getting at, like they wouldn't want to
Yes.
explore. So you're going to shut down the whole exploration system. But that's not what you want to do. You want students to explore and make mistakes and learn from their mistakes.
Yeah.
So I think it's important that they should know that it's okay to make mistakes and how we can learn from them.
Yeah, that's exactly right. I think, the um, feedback here is important because unlike the zebra finch experiment where the brain itself is self-correcting, in an education context, it is possible that the student does not know, if it was a mistake or not, because there may not be any feedback.
Yeah, exactly. Sometimes sometimes they may not know, but you'd be surprised. Like often, if you watch kids, I think they're natural scientists. A lot of children, like the way they explore the
Yeah.
world, I think is very close to what professional scientists actually do. We're just a little bit more organized. But if you watch kids, they often come up with hypotheses about what might happen, and then they try various things, and they learn how the world works. And I think that natural trial and error learning
Yeah.
process is very powerful. But I think, as you said, a lot of formal education tries to shut that down.
I shut that down. Yeah, so it has some implications. So, in conclusion, Vikram, I know that you're looking at other possibilities here. So, what would be your sort of next area of focus in this arena?
Yeah, so we're actually very excited about looking at the female songbird. So this again goes back to your previous question, right? So everything we've talked about so far is how you evaluate your own performance, right? So you're learning how to play a song, you're listening to yourself, you're evaluating yourself, and you're learning from your mistakes,
Yeah.
right? And then we talked about performing this in front of an audience. Now the question is, what is the audience doing,
Yeah.
right? So right, so if you go and listen to a music concert as a member of the
Yeah.
audience, you are also evaluating the performance in some way, right? You like certain performances, you don't like certain others. What is happening in your brain while you're listening to a
Mm.
performance? That is something that we know very little about,
Mm.
right? And again, the songbird system is a really cool system to ask the question from the perspective of the audience, because as I was saying, these male birds, they learn to sing so they can perform to a
Yeah.
female, but the female needs to evaluate the male song and decide if that song is attractive or
Right.
not, right? And these birds are socially monogamous, so which means that if the female thinks that the male song is attractive and decides to mate
Yeah.
with him, then she's going to pair up with him for
Right.
life. And so this decision whether to mate with him or not, depending on whether she finds his song attractive or not, is perhaps one of the most important decisions she will ever make in her
Mm.
life. And yet we know very little about how she's actually doing this. What is going on inside the female brain?
Yeah. So this goes to, again, is there some sort of information content in the song,
Exactly,
right? Yeah.
exactly. This was what you brought up really early on, and yeah, and I asked you to hold that thought because because we're going to come to it. And yeah, thanks for reminding me. So exactly, what this is sort of an age
Yeah.
old question, right? Like from poets and philosophers alike have wondered, what is the purpose of birdsong, right? You're walking along a park and you listen to all these beautiful songbirds singing, and you ask yourself, why are they singing? What is the purpose? Are they communicating something? And so it's a very deep question in some sense. And so we're beginning to have certain clues about what might be going on. So for example, in zebra finches, as I was saying, the moment a male sees a female, he goes into this performance
Yeah.
mode, right? And one of the characteristics of the performance mode is this reduced
Yeah.
variability. So the song becomes extremely
Right.
stereotyped. And it turns out that the female also likes to listen to stereotyped
Mm.
songs compared to variable
Right. Yeah.
songs. So she cares a lot about whether the male can hit the same note again and again in exactly the same way.
Right.
Right? And so we know this from behavioral studies. And so the idea, or this is a speculative idea, but one idea is that it's very difficult to produce a stereotyped complex motor
Right.
sequence, right? And if you can produce a complex song in exactly the same way again and
Yeah.
again, that speaks to something about the quality of your neural
That's
circuits. So it is an honest signal of the quality of the male's brain, just being able to do this.
right. Exactly. So, if you look at other exhibitions in the courtship context, like feathers and other type of things, there
Right.
is always a question of health.
Exactly.
And
Exactly.
that is sort of a decision factor, right? In there. So yeah, so that makes sense to me. That yeah, if you can reproduce something, there's aspect of memorization there. There's an aspect of skill, and
Right.
overall
Exactly.
that points to a better male. Yeah.
Exactly. And I think even in humans, we often like good musicians, of course they need to be able to do much more than produce the same song in exactly the same way. We can talk about improvisation and creativity and all that. But at a fundamental level, it's hard to be a good musician if you're not able to keep the same beat in exactly the same way, right? And I think that at a fundamental level is speaks to the quality of your brain, of your neural circuits. And so that's a very compelling
Yeah.
idea. It's pretty speculative, but I think in terms of the evolutionary angle, I know that you're interested in the evolutionary angle of things, and you
Yeah.
often ask about selection pressures and stuff. So in terms of
Yeah.
sexual selection, this could be why the females are interested in that, and why the males are going out of
Right.
their way to produce this stereotyped song.
Yeah. So one interesting question also would be is the female interested in lower variance and less concerned about the content? I don't know, this is
Right.
measurable, but if the female is really measuring the male's ability to reduce variance, and that is obviously that means that it is able to learn systematically. Maybe
Right.
the content itself doesn't matter. In other words, suppose you train a male bird with an error in the seed, right?
Right.
Does the
Right.
female
Right.
actually accept that, even if the male is
Yeah.
able to produce that over and over again without any variance?
Yeah, that's a very important and complex question. And I think there are no simple answers here, but I will say that there are a few different ways in which you can look at this. So you're absolutely right in one sense, because so let's see, what is the male trying to do, right? The male is trying to make a copy of his father's
Yeah.
song, right? So he's trying to sing as similar to his father as he can.
Right.
But the female might never even have heard of this male's
That's
father's
right.
song,
Yeah.
right? So when she listens to the male song, she might be more interested in how he is singing
Right.
the song than what
That's
exactly he is singing. So it might matter less which song you pick
yeah.
to sing, and more important, how well you sing
Right.
it,
Right.
right? But on the other hand, it can also be argued that the content is important, because if you sing an extremely
Hmm.
simple song, then it might not be very impressive if you sing it in exactly the
Yeah.
same way.
Yeah.
If you have like a song with a single syllable, then with no complexity, then it's almost like stuttering. You're just making the same sound again
Right.
and again, but that might not be very impressive. So I think it is a combination of complexity and stereotypy that that the female is looking for. And and I should also say that this is with zebra
Yeah.
finches, right? There are other birds that have very different systems. So the zebra finch is a very simple songbird, if you will, and it's great for neuroscience because it's simple. So it has a single song, it never changes that song, and it just sings that same song for all its life. But there are other songbirds that have, like nightingales, that have many different songs. Some songbirds have hundreds of songs in their repertoires, and they can pick and choose which song to sing to which female, and they can really put on a show. And so those females might, be evaluating something much more complex than what the zebra finch female is doing. But I think that this is a great entry point because of the simplicity that we can start getting at some fundamental principles of how we evaluate the actions of others. And then once we have that understanding, then we can increase the complexity of our questions.
Yeah. Excellent. Yeah, this has been great, Vikram. Thanks so much for spending time with me.
Thank you so much for having me.
You. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.